So, a very interesting analogy to start with when we're talking about electric potential would be sort of topography. And if you have ever done any hiking and have looked at sort of trail maps, topographical maps give us a way of visualizing a three-dimensional space in two dimensions. And often when we're dealing with vector fields like an electric or magnetic field, and so far we've only dealt with electric fields and to a lesser extent gravitational fields, although more just talking about gravitational force, we have been doing that. So one tool for visualizing something 3D in a two-dimensional space is by sort of translating it into this kind of map. So the main thing here is when we're talking about vector fields, we're going to talk a little bit about the gradient. And the gradient is just the sort of derivative, it's a three-dimensional derivative of a vector field, or sort of the topography of a vector field. And once we take the gradient of the potential, we'll get electric field. Now, the whole point of doing this is that although it's very I guess, easy to conceptually understand electric fields, or it's easier to conceptually understand electric fields, it's very difficult to measure them. And this is why when we do the lab, we don't actually do any direct measurement of electric fields. We do have a lab where we have a direct measurement of an electric potential, and that's because that's voltage, right? So we have all kinds of tools for measuring voltage, and we have lots of things measured in voltage because that is the easiest way to go about it. So when we're dealing with electric potential, let's say we have positive charges like this. We'll call these source charges, and then we'll have some other charge we'll call Q that is just a charge that's not related to the source charges. Now, this is picked arbitrarily, but just for the heck of it, we're going to start with electric potential energy. And potential energy we're already familiar with. So the way that we go back and forth between energy, potential energy, and potential, which is kind of a misnomer, that's the voltage, is we multiply our potential, meaning our V or voltage, by our charge. The potential energy is the potential energy of the entire system, whereas V is actually the potential from the source charges, and Q would be the other charge, so regardless of the other charge. So electric potential, we can figure out if we have some charges, what does the topology, see these lines are a lot like the topographical lines we just looked at, look like everywhere in space. And then if we add a charge later, we can figure out what the potential energy of that system is based on that. Now the units of potential, electric potential, which is not an energy but is closely related to an energy, are in volts. And a volt is sort of a joule per coulomb, joules being a unit of energy and coulombs being a unit of charge. So when we add this charge Q back, now that's where that charge Q is. So we get this distribution, these equipotential lines, this map from the source charges and therefore the electric potential. And then if we add another Q, we can get the potential energy. The other thing we want to sort of address is this is what you'll see in the book. You can get electric field from potential, and it's the derivative of electric potential, V in volts, with respect to space. And we did this in the lab, and there's a negative sign here, which is pretty important, but just for the sake of it, here we have this derivative, and electric field has units of newtons per coulomb or volts per meter. Here you can see volts per meter makes most sense because we're doing basically volts over distance, if you think about this derivative locally. More formally, however, like I said, this is a three-dimensional thing. So electric field is usually a three-dimensional field, and therefore, in order to get 3 dimensions from a scalar, we have to have this crazy three-dimensional derivative. And the way this works is this is a partial derivative of the potential with respect to x in the x direction, and then you take another partial derivative with respect to y in the y direction, and you continue with z. So that's how you contain a three-dimensional vector value for electric field within one scalar by doing this 3D derivative. You can also write this in spherical and cylindrical coordinates, and here it is. You don't actually need to know this specifically for this class, but it is very useful because remember, we are talking about three-dimensional things. So when we scale down to one dimension, it's simpler, but it doesn't give you the whole picture, and that wouldn't give you that whole 3D map. So that's sort of my intro for this chapter, which is on electric potential. Electric potential is really measured in volts. That's why there's this battery back here. And here's what we're going to go over. We're going to talk about potential energy, then we'll talk about the potential, then we'll talk about ways of calculating it, going back and forth between electric field and electric potential, and then we'll talk a little bit about sort of the geometry of equipotential surfaces and potential gradients.